Good morning. I'm Paul Bierden. I'm the president and CEO of Boston Micro Machines Corporation, and I'll be talking about MEMS deformable mirrors. First, a little bit about the company. We were founded in May of 1999, so we're just about at our sweet 16th birthday. We're located in Cambridge. The technology was spun out of Boston University's Photonics Center, where we still have a close relationship. The products that we work on are MEMS mirrors for beam control applications. We develop advanced optics and imaging systems. We also do contract R&D, both government and commercial and corporate. We are a small business. We have 13 full-time equivalents. In terms of our revenue, we're broken up in fiscal year 14. We were 40% contract, 60% revenue. That's about average. We fluctuate about 50-50, plus or minus 10%. Our customer base is made up of university labs doing a variety of different research. We also do work with different kinds of labs like NASA astronomical research labs. We work with other national labs and university research labs for a variety of imaging applications. And we have customers ranging in size from large defense contractors to small instrumentation companies. Overview of our technology. As I said, we make optical MEMS, mainly deformable mirrors, for wavefront control and imaging applications. We do modeling, design, defining of manufacturing processes. We do test and integration. Our TRL is in the 2 to 4 range, maybe 6, and I'll say why maybe 6 a little later on. We have right now 3 different ongoing NASA-funded programs, 2 SBIRs and a TDEM program. The SBIRs are to improve our existing deformable mirrors for space applications, both in topography and reliability. And the TDEM program is to advance the technology readiness level of the devices. We have past projects. The company was actually founded on a NASA STTR. That's what kicked off this company. So we've done a number of NASA SBIRs and STTRs, as well as an APA program. These have all been for different kinds of mirror developments, or new mirror development, or mirror enhancements for specific applications. So a little bit about why we make these mirrors. And so a quick primer on adaptive optics, in the field of adaptive optics. So in adaptive optics, you have light coming in from some object you're trying to image. The light is aberrated, and your adaptive optics system consists of a deformable mirror where the light bounces off of and goes to a high-resolution imaging system. Part of that light is broken off and goes to some kind of wavefront sensor where you'll detect the phase of the light and the aberration of the light, closed-loop control to send back to the deformable mirror to compensate for that aberration. The aberrations are introduced through a variety of different fields just based on what you're trying to look at. So for ground-based astronomy, your aberrations are introduced through the atmosphere, the moving of the atmosphere. For space-based astronomy, your aberrations come from thermal effects, so slow thermal effects, or the optical tolerance of the manufacturing. If you're doing biological imaging, so as opposed to looking up, you're looking down, those aberrations are introduced through the tissue that you're trying to look through. What Boston Micro Machines works on is we make the deformable mirrors. So we make a key component in an adaptive optic system that can actually control the wavefront. The way we do that is through a Surface Micro Machines MEMS device. MEMS is micro electromechanical systems. And our mirrors consist of an array of actuators, anywhere from a 6x6 array to a 64x64 array of actuators. They fundamentally work by, this is just a cartoon of 3 actuators. There's an electrode on the bottom, an actuator over each one, and then an attachment post that goes to a mirror sheet on top. As you apply voltage to the electrode and your actuators are grounded, electrostatic force pulls the two of them together and subsequently will change the shape of the mirror surface. Over here you can just see the actuator deflected, and then on the right is the mirror surface. This is an interferogram of the mirror surface with one actuator pulled down, showing kind of the smooth change in shape of the mirror surface. And here's just a little movie of a cross sinusoid pattern that's put onto the mirror surface. You can see kind of what resolution we can get and what kind of control you can get on the mirror surface. The way these are made is in a process that's similar to the process that's used for semiconductor chips, just about 20 years old technology. It's made of subsequent layers of depositing structural layers, patterning and etching, and then putting sacrificial materials on top of that and repeating that process. So we start with a silicon wafer. We use 6-inch wafers. And you deposit a layer of polysilicon and pattern it to make the electrodes and all your wire traces for electrical connections. After that, you're depositing a sacrificial material. We use phosphosilicate glass. And then another layer of structure, which is our actuator. After that, we repeat the process, put another sacrificial layer, and then structural layer, which is the mirror. And now you have a wafer with a bunch of die, and these are all nice and solid. These are blocks. The die are diced up. You take the die and you put it into hydrofluoric acid. When it's in hydrofluoric acid, all of your sacrificial material, all your oxide goes away, and you end up with a released structure. So now you have a three-dimensional structure that can move up and down. These parts come back. We then put a metallic reflective coating on it. We put it into a package, and that's the device. That's the deformable mirror. We have a number of different mirrors out there. So to go through a few of them that are specific for astronomy applications, first one is our Kilo DM. So it's about 1,000 actuators. We have a couple different configurations in terms of square or circle. And the stroke is between 1.5 microns and 3.5 microns, depending on the application and the size of the aberration you're trying to correct. We have a 492 actuator device, which is basically the same device, just scaled down. It's half the size. One of the outcomes of one of the latest SBIRs was a 2,000 actuator device. This has 2048 actuators. It's 40 actuators across the aperture on a 400 micron pitch, so you have a 20 millimeter active area. So that's the kind of scale of this. So this over here is about 20 millimeters. This has 3.5 microns of stroke, and unpowered, it has a surface figure of about 90 nanometers RMS. We can flatten that down to about 12. But this was a direct outcome of one of the SBIR programs that we're working on right now. Another SBIR program that we finished recently was to develop a tip-tilt piston mirror. So for this, normally our actuators are in a Cartesian grid. And to make this device, we took every other row and moved the actuators by basically half a phase. So now you have a triangular pattern, and when you have a triangular pattern, you can make that into a hexagon. So the mirror surface will then cut into a hexagon, and that gives you then tip, tilt, and piston control over each of these segments. So there's 1,000 segments with 3,000 actuators underneath. This doesn't have a lot of tilt. This isn't a galvo. This isn't a scanning mirror. This gives you about a half a degree, but a half a degree at very high precision. Our step sizes are sub-nanometer step sizes. So you're able to get very high precision angle control. And this was delivered to JPL in 2013. So our ongoing NASA programs are for space imaging applications. So the first one I want to mention is topography improvement. Our mirrors are relatively flat, but if you remember the manufacturing process, it's layers upon layers that are built up. And these are thin layers. Our thickest layer is 5 microns. They're normally about 2 or 3. So any kind of a gap goes over and it propagates up through the manufacturing process, and you end up with print-through or remnants of underlying structures on your mirror surface. And you can see that here. These lines are on the mirror surface. You can see them in the mirror surface, but they're actually due to the actuator layer underneath. This gives you this is about a 600 micron square area, an RMS value of 13 nanometers. These are very small, they're about 10 nanometers deep, but they are giving you an effect on your roughness and the diffraction of light coming off. Our new process that we have goes over and eliminates that print through, and you end up with about a 2 to 3 nanometer surface figure. Why this is important is when you're doing high contrast imaging applications. So normally an optic with 13 nanometers RMS is going to be a good optic, but when you're doing high contrast imaging, the diffraction peaks that are coming off of those regular patterns spill over into your nulls. And they're hard to get rid of because it's an uncontrollable error. There's chromaticity in the diffraction orders, so it makes it more difficult to go over and to get these deep nulls. And a photon in the wrong spot might look like a planet, but it's not. And so we want to make a smoother surface. The other program we have going on is enhanced reliability. So it's hard to go over and to say that you don't have reliable devices. It's not a good sales pitch. But when we do, our devices are reliable. We actually have done about 13 trillion cycles. The devices run for a long time in a controlled environment. But they do in turn sometimes fail. This can be due to a transient voltage spike, a one-time error that's coming in. And if it's in a lab, we can go over and take another mirror off the shelf and send it to a customer. But if it's in space, you can't do that, obviously. So what we have is we have some redundancies that will go over and hopefully compensate for any kind of spike in the electronics. A cosmic ray causes some electrostatic charge. So these are ways that we're trying to solve that issue. What we're doing with that, you can see the cartoon here of, this is our heritage design. And what happens is if this voltage applied to the electrode, if it passes over some critical voltage, your actuator is going to snap down, it's going to touch. When it touches, you now have a short, and probably about 95 times out of 100, that actuator is now going to be non-functional. You're going to have grounding, you're going to have an arc, it's just not going to work. And so what we've done is we've modified our design. Just very simply, we made a hard stop, so a mechanical hard stop, so a small micron tall cylinder, about 2 microns wide, sitting on our device. And then we put a ground pad on the center. So as you're going over and you're passing your critical voltage, the mirror will touch down, it's grounded upon grounded, so no discharge, and you're able to go over and survive that kind of a one-time spike through. Here you can see this is our design. There's actually 4 hard stops across the actuator. This is a layout of the electrode where you can see the 4 points where those hard stops are going to touch down. And to prove this out, while we pitched this as this is to stop one-time failures, kind of intermittent things that might go through, we went through and did 3 million cycles where we went past the critical voltage. And so those would have been times when 3 million actuators would have failed. But we can see that this is applied voltage versus deflection of the actuator. And after 3 million cycles, it follows the same curve. It survived all 3 million cycles. We have goals of about 50 million cycles. We're not quite there yet, but 3 million should probably suffice if you're just trying to do those one-time rogue failure modes. Another ongoing project we have is a TDEM program to improve the TRL of our devices. As was said earlier, we are in that valley of death. We had the cool new mirrors. People are excited about them. People were testing them. And then someone said, I want to put it into space, but we're not at TRL. So there's a really boring, well, it's not as sexy as going over and making new devices. We're going through environmental testing right now. So we have a series of devices that we're manufacturing, we're characterizing. Some of them are going to go to JPL, some of them are going to go to Princeton. They will characterize them in their high contrast test beds. We'll then go through environmental testing to simulate launch. We'll do shock, vibration, acoustics. Then they'll go back to Boston Micromachines and then back to those other labs to show that how they survive. There's a series of devices that are being made that are going to go through a series of different testing. Since we don't know exactly what kind of launch vehicle it's going to be, we went from something that's very easy that we're really expecting it will pass, all the way up to something that there's a good chance it'll destroy the mirrors. But that will give us the idea of the window as to what we can operate in. Some observatories that have our devices right now. So that was the kind of work that we're doing for NASA. Now, let's just go into some places that are actually using our devices now. These are some observatories that have our devices that are on sky right now. There's the Lick Observatory, which is doing some visible AO. They started off with our small device, which is a 12 by 12 device, and then have scaled up to a kilo DM, sorry, a 32 by 32. The Palomar Observatory is also using our small DM in what's called Robo-AO, which is an autonomous adaptive optics system. I think the movie just ended, which was kind of a fun movie, but that's okay. What Robo-AO is it is a bolt-on adaptive optics system. It has a laser guide star. It has an adaptive optics system. It goes on about a meter-class telescope, and it will then go over and throughout the night go and automatically go to different points that you've programmed, do the adaptive optics, and do the imaging. This was spearheaded by Christoph Beranek, who's now in Hawaii, and it's a plug it in and let it go. And it will go over and it observes, I think the most they did was somewhere around 60 to 70 objects in one evening. And Christoph will say this, I'm not making fun, as he sat there and watched Netflix, because it was able to completely autonomously go over and do all those observations. And then the last here is the Table Mountain Observatory that's doing Natural Guide Star Adaptive Optics in the Kapow program. Moving on to some of our larger devices, this is the 2K device. This is the SCEX-AO, the Subaru High Contrast Imaging, or Extreme Adaptive Optics. They're using our 2K mirror, which can be seen in the system here. They have some lab results right now showing that they've been able to improve the STREL from about 25% to 95%. Earlier, they had used the Kilo DM and had gone on sky with that with good results. They scaled up to the 2K system. I believe they were supposed to go on sky in January with the 2K system, but weather prevented that, and they're going back on sky in April. And then finally, in terms of what's on sky right now is the Gemini Planet Imager. This was a program where we were making a 4,000 actuator device. It took us a number of years to get that. And that's been put on into the instrument on the Gemini South Observatory. First light results came out in November of 2013, where they were actually able to get light back from Beta Pictoris and do some imaging in terms of the polarization and imaging of stars with different disks. So it's been a good program for us. It was a lot of hard work that went into making that mirror, but it's on sky, and the GPI group are doing some really good results right now. I'm getting some good results now. So one other system that we had was, this was the picture program. This was a sounding rocket program that was run, had included in it Boston University, Jet Propulsion Lab, UMass Lowell. And so this was a sounding rocket. The telescope was to go up, look at Epsilon Array, observe for, I think, 300 seconds, and then come nice down to Earth perfectly. The telescope went up, it did something, it came back down. The one thing it didn't work was the telemetry didn't work. And so we don't know what happened when it went up there. And then it came down, and it's a long telescope, and it fell over, and the primary mirror shattered. And so there's another Picture 2 program coming out in hopefully soon. They've been developing the new instrument. But what this resulted in is one of our deformable mirrors went up into space. It did work. It came back down again and survived. And so that's my point of potentially TRL-6, because it went up and came back. We just don't know how well it did when it was up there. There's also a number of test beds that are using our devices for different kinds of designs and tests for next generation astronomical instrumentation. So we have them at NASA, NASA Ames, Space Telescope Science Institute, two different ones in France and Paris, and then in Nice. It's, as I mentioned before, it's at the High Contrast Imaging Lab at Princeton. So there's a number of groups that are already using devices that are our products that are being baseline for the next generation instrumentation. And just to skip away from the telescope and do a couple other applications that we have for adaptive optics. So this is an exciting one for us. This is called superpenetration multiphoton microscopy. So as opposed to having an instrument that's looking up at the stars, you flip that around and you have an instrument that's looking down into some biological sample. And what this is a multiphoton instrument where the deformable mirror is here, and you're going over and you're imaging into a mouse brain. So this is in vivo imaging of a mouse brain. Why this is special is because we are actually imaging through the skull. Normally when you do this, if people are squeamish, I'm sorry, they'll take off part of the skull, put a glass plate on there, and image through the glass plate. This allows you to go over and do that imaging without removing the skull. So you can go over and what was here was imaging of neurons going about 1 millimeter deep into the brain, into the mouse brain, which is very deep in terms of trying to get through a fairly highly scattering media of a skull and getting into it. And then the bottom one was, I don't know if you remember, it was a false color, red and green. Those green flashes were actually neurons firing. So this was actually functional imaging of a brain. So yeah, so this is going deep into tissue, going down about 1 millimeter. And over here, those green flashes are neurons firing. The mouse is thinking about something. And this work was being done at Genelia Farms, so not far from here. Another application of adaptive optics, which has some heritage to it, is in retinal imaging. So when you're trying to go over and look at the retina in the human eye, in vivo imaging, turns out your eye is a fairly bad optic. And so you can use adaptive optics to compensate for both the static errors of your lenses and then all the dynamics of the vitreous humor in your eye. And this, using this adaptive optics, you can get cellular resolution imaging. So this are the photoreceptors that you learned about in biology. These are all about the order of 2 microns. And then here is a microaneurysm. So this is actually a microvessel, and each one of those white streaks going through is an individual blood cell going through the smallest vessels in the eye. And then this is a small aneurysm, a little bubble in the vein, in the vessel. And you can actually see the blood, how it circulates through that microaneurysm and then comes out again. And these are in vivo. It's a non-destructive testing because this is my eye. That's actually my microaneurysm, and those are my photoreceptors. So why is MEMS mirror development important? We've made some steps. Why would you want to continue on with this? Well, key things are the Decadal Survey of Astronomy #2 was seeking nearby habitable planets. I'm preaching to the choir here, but that's why. And high contrast imaging and exoplanet detection needs adaptive optics and needs really high quality deformable mirrors. And we're close, but we still need to go over and work on getting better DMs for that real challenging application. For the extremely large telescope, the TMT, the EELT, the GMT, these are some of the first telescopes that are designed that have adaptive optics as mandatory requirements. Because they're so large, they need adaptive optics. All first light instruments that are planned on those telescopes have AO. None of them have MEMS mirrors because these are all large adaptive optics programs, but not first light instrumentation, but first generation instrumentation, all will be needing high actuator count DMs. And then the last thing is the White House, the BRAIN Initiative, the brain research through advanced innovative neurotechnologies. We've been working with that. We have new ways. The functional imaging of a mouse brain is one of the goals of the BRAIN program. And so we're trying to go over and work with groups to be able to do that. So in summary, BMC has a core strength in the design, manufacturing, and integration of MEMS mirror systems. We have provided and continue to innovate deformable mirrors for exoplanet detections, and we're committed to developing this technology for a variety of markets. Thank you. Any questions?
In your environmental testing that you're recently doing, have you found it behaves differently with vacuum or thermal, that you're seeing any need to change the design for the stronger environments?
Vacuum, we don't see a problem with. The only issue with vacuum is the devices are over-damped by squeeze film damping. So you have small gaps, and the air acts as a spring, and so they move much more slowly in air. And in vacuum, they're very much underdamped, and so there's ringing afterwards. The group at NASA Ames has been testing for about a year now our devices in vacuum in their test bed, because they really want to get all environmental conditions out. So they've been testing in vacuum without a problem.
Okay, because I had worked on I had another MEMS device that actually had a problem in vacuum, and it was stringing like a guitar string, and then we had to do a seal change. But I was just curious, so you're not having any issues?
No. I mean, it definitely rings,
yeah.
but it'll settle after a millisecond or two.
Okay, and how about thermal?
Thermal, they're not bad in thermal because they're all of the same material. One of the biggest problems that we've had with thermal is the CTE mismatch between the package that it sits in and the silicon chip, because there's a silicon wafer and the silicon structures on top of that, so they move kind of uniformly. So we've worked with having a low modulus attachment process, work it kind of like just to take up any kind of CTE mismatch.
Okay.
So. But then you're having the issue of, you have something that's an elastic attachment, how well does that survive a shake test? And so we're trying to balance that out.
Okay, thanks.
Oh. Any questions?
How about high-power laser applications? Have you developed any devices for that?
High power is in the eye of the beholder. High power means different things to different people. If you're thinking of truly high power, like a directed energy application, these aren't the devices for you. The mirror surface is a 3-micron thick piece of silicon with some kind of a 98% reflective coating on it. It'll vaporize the mirror.
Question, but is there a lockdown mode during launch or something? Lock them all down?
No, because they never actually touch. And so it would be, you could apply a voltage and it would stiffen it some more, because they actually do stiffen as they're bending. But we're not as worried about the vibration testing, because the natural frequency of these devices is about 70 kilohertz. And they have no mass. I mean, they're thin films, and so there's no mass, so there's a little inertia. So we're not worried about the vibration aspect of the mirror itself. Thanks. Any other questions? Okay, thank you.